Okay. So for mixing problems, this is the type of section. This section deals with mixed problems involving a mixture of content. A lot of focus on concentration of a solution containing water along with a substance that's dissolved in it. Generally speaking, is I guess how you could describe them. And sometimes you'll be diluting a substance, meaning making there be less content in a tank, and other times you'll be adding more over time. But the general goal is like they're all very similar. And these several examples. So a tank contains 100 gallons of pure water. At time 0 you have sugar water solution containing 0.2 pound of sugar per gallon entering the tank at a rate of 3 gallons per minute. So it's originally pure water, 100 gallons of it. Now we have sugar water entering. And a drain is opened at the bottom of the tank, allowing the sugar solution to leave the tank at 3 gallons per minute, so both of these happen at the same time. Then we assume that the solution in the tank is kept perfectly mixed at all times as an addendum, and I think that's a general rule for these types of problems anyway. Will be the sugar content in the tank after 20 minutes. So we can't solve this yet. We have to first do a lot of setup. We basically have to find we have to create a differential equation and solve it for the amount of sugar at any time t. And from there we can maybe perhaps find out our answers to this question. So we allow x at t, the equal number of pounds of sugar in tank after t minute, and this applies always. X at t will be generally, for these types of problems, your amount of sugar or salt or any type of mixture in it, any type of the solute, something that's being mixed in it. And v at t will be the volume of mixture t minutes after starting time. And this is just general rules for it, how we'll define them. And the v dt is the change in volume over time, which is 3 gallons per minute minus 3 gallons per minute, which is equal to 0, since meaning, it's constant volume. It's given. Because rate of change is rate of something in minus rate. No. Rate of mixture in minus rate of mixture out, basically, is the change in something. In general, that's how it works. And that's how we do it here. So it's, and dx dt is rate mixture in minus rate mixed out. And in this case, basically, since we have constant volume first, before we talk about that, we have the constant volume because the rate is in as it goes out the same rate. So that means v at t is equal to v0, which is equal to 100. That's important, because as you'll see, we need that when volume, whatever the rate of volume is at time t matters. But it's always going to be just a simple constant 100. So the rate mixture in, it's dx dt, so it's basically the pound per time t, which is minutes in this case. And we have pounds of sugar per gallon, so that's pounds per volume basically. So what we do is pounds per volume times the volume per minute, and that gives us dx dt. The unit's correct. It allows us to convert our 0.2 pounds per gallon to 0.6 pounds per minute when you multiply by 3 gallons per minute. And then the rate mixture out is x at t divided by v at t, which is a note in pounds per gallon to make sure you understand the units, and multiply by 3 gallons per minute to get rid of the gallons. So it's basically we're subtracting 3 times x at t divided by v at t. And v at t is just 100, so that's why I substitute that in pink. So in the next step, so we have the x dt equal to 0.6 pounds per minute minus 3/100ths times x at t pound per minute. And I eventually simplify this down just to x prime equals 0.6 pound per minute minus 0.03 times x at t pound per minute. And this is the linear ODE. And a better way of writing this is just x prime equals negative 0.03 x plus 0.6. We can solve for x at t. We have the a term as negative 0.03 and the f term of 0.6. U of t is equal to e to the negative integral of a, so dt, a term dt. So it literally is just 0.03t. Very simple a term, so it'll just be, a is just a constant, so it'll be a constant times t basically. Then you do integration like normal. Just like in the last section, we do this linear ODE like before. With the integrating factor. In integrating factor, we have to have x at t equal to integral u at t times f at t dt divided by u at t. So we have the integral of e to the 0.03t dt is what we want to evaluate. And we just do v substitution. Very basic at that point. It's more of at this point, sometimes it's more of an assurance to make sure you write it all out, just to make sure you show your work, and also because it's a good way to double check. So you eventually do arrive at e to the 0.03t divided by 0.03 plus c. I mean, in general, that's how an integral, if you have e raised to a power times t or x or whatever, if you integrate that, it'll be the same thing divided by it, by whatever it was raised to, like, pretty much. In this case, it was raised to 0.03, so it's going to be divided by that. But it's always good to do it this way to show it. But that's just something you notice after doing it multiple times, this type of substitution. So as our integral solved, we go, with our evaluation of the integral, we go plug it in. And then it's simply 0.6 divided by 0.03 will be 20. And e to the 0.03t will cancel out on the left hand, on the left part of the term. And in the end, it's just 20 plus c times e to the negative 0.03t. And at t equals 0, we have 100 gallons pure water, which implies that x0 equals 0. There's no salt. There's no sugar in this case. There's no sugar, so x0 equals 0. And that means that 20 plus c to the e to the 0 power basically is equal to 0, so it's c times 1 essentially equal plus c plus 20 equals 0, so it's c equal negative 20. Going from there, we plug it in, and then so x at t equals 20 minus 20 times e to negative 0.03t. Then we plug in the question asked for A, just what will be the sugar content in the tank after 20 minutes. So we plug in, since t is in minutes, just 20 in this equation, and we get our answer as 9.024 pounds. So that's the sugar content, 9.024 pounds after 20 minutes. How long will it take sugar content in a tank to reach 15 pounds? Yeah, it's gradually increasing over time because we're adding sugar solution to the tank. So it'll just continuously increase to a certain point. Eventually, if we go at infinite time, which is part C, it'll eventually reach a certain point where it won't increase anymore. But it's on an increasing path. It's not decreasing at all, was how it's set up. So we can just set, we have x at t equal to 15. And we want to know what t equals then. So we solve for t when x at t equals 15. So 15 equals 20 minus 20 times e to the negative 0.03t. Basically we subtract 20 and then we divide. To get e by itself, we put a natural log. Alright, so then eventually we get t equal to 46.2 minutes approximately. And then finally, what will be the eventual sugar content in the tank? For part C. Well, we take the limit of x of t as t approaches infinity. And it's just 20 minus 20 times 0, which is 20. Because it becomes 20 minus 0. And basically, this is due to the limit of t approaches infinity of e to the negative infinity, which occurs, is equal to 0. So 20 pounds of sugar is the answer. That's the most it'll ever get to. So this one is the tank initially contains 50 gallons of sugar water having a concentration of 2 pounds of sugar for each gallon of water. Time 0, pure water begins pouring into the tank at a rate of 2 gallons per minute. Then we have a drain is open at the bottom of the tank so that the volume of sugar water solution in the tank remains constant. So yeah, the VDT is going to be 0 again. In most of these it is, for several of these. So the first is A, how much sugar is in the tank after 10 minutes. I drew this diagram just in case. You can always draw this if you want. I don't find it particularly necessary because it's not that hard to keep track of a couple details only when writing it out. But it can be a good visual guide, like always, to draw a picture for some of these real world problems and stuff. You have 50 gallons in the tank. 2 pounds per gallon times 50 gallons equals 100 pounds. And that's our initial quantity. Enters 2 gallons per minute, leaves 2 gallons per minute. So V0 equals 50 gallons, and that's what V T will always be, 50 gallons. So rate mixture in minus rate mixture out is how we handle these for both of them. So dx dt is, we can write this as x prime equals 0 minus x of t v at t times 2 gallons per minute like before. Its rate mixture in is 0 because it's pure water in. So x prime is equal to negative 2 times x over 50, or x prime equals negative 1/25 x. So dx dt, we can rewrite it as just dx dt because we're going to use separation of variables, is equal to negative 1/25 x. Because this is very easy to solve by separation of variables. We don't have to do any, it's not a linear ODE like before. It's not the type we have to worry about. So we set it up and do separation of variables. We have our natural log of x, like which normally develops. And negative 1/25 t plus c and stuff. So it gets solved for, and the absolute value is dropped, of course. So x of t is equal to a times e to the negative t divided by 25. So we have 100 pounds, I rewrote it like 50 gallons times 2 pounds per gallon, so it's 100 pounds of sugar again. The next ones have solved, I think. So x0 is 100 pounds, so 100 equals a times e to the negative 0 divided by 25. So it's, so that's e to the 0, which is 1, so it's a equals 100. So x of t is equal to 100 times e to the negative t divided by 25. Oh, and finally, it asked originally how much sugar is in the tank after 10 minutes. So x of 10 is equal to 100 times e to the negative 10/25. You plug it in, you get 67.03 pounds. How long will it take the sugar content in the tank to dip below 20 pounds? Like the last one, we solved this. X of t equal 20. What does t equal? So we solve for t. 20 equals 100 times e to the negative t/25. So, and you get 40.24 minutes. Finally, we have what will be the eventual sugar content in the tank. Take the limit as t approaches infinity. X of t. So this, I even did it a little bit more different. I did it show off the work. It's 100 times the limit of t approaches infinity because 100 is a constant. So it's 100 times the limit t approaches infinity of e to negative 1/25 times t. This is equal to 100 times e to the negative infinity. Plug in t. So it's equal to 100 times 0, which is equal to 0, so 0 pounds is the answer. So there'll be no sugar left, basically, eventually. As t approaches infinity, there'll be no sugar left. Okay, so a tank initially contains 100 gallons of water in which is dissolved 2 pounds of salt. We have 1 pound of salt for every 4 gallons of solution entering the tank at a rate of 5 gallons per minute. And we have the solution leave the tank at the same rate, so we have constant volume, as it says, constant solution volume. Again, so volume will be constant, so we'll have 100 gallons. And I wrote in diagrams, 5 gallons per minute times 1 pound per 4 gallons. So 5 pounds per 4 gallons is dx dt, like that's what's coming in. So it's 5 fourths minus 5 gallons per minute times x of t, 100 gallons. Basically. Yeah, it's x of t over v of t is a common expression for these ones. So when you have an unknown rate. So it's 5 fifths minus 5 100ths x of t is what x is equal. So x prime is equal to 5 fourths minus 1 20th times x. We have a equal to negative 120 and f term equal to 5 fourths. So the integrating factor, we solve this because it's a linear ODE, a linear ordinary differential equation. So we have very quick to integrate. It's e to the t divided by 20. We have to integrate that though next, and easy enough. Since we've done this before, just a quick v substitution method. No, it's just the setup. You just have to be able to set it up is the main trick to these and know what to do with them. The actual integration work is nothing new on this section. So just be calm and collected while looking at this. Eventually we arrive at 25, x of t equals 25 plus c times e to the negative t 20th. And we now know x of 0 is equal to 2. So it's 2 equals 25 plus c times e to the 0 power. So it just becomes 2 minus 25 equals c. So c equals negative 23. And that's our formula. X of t equals 25 minus 23 times e to the negative t 20th. Now the question is, we want to use an analytic method to determine the eventual salt content in the tank. So we're just going to take the limit as t approaches infinity, and that'll give us the answer on this formula for salt content. It becomes 25 minus 23 times e to the negative infinity. So it's 25 minus 0 eventually, so it's 25. So salt content will become 25 pounds, and that's the question over. Answer 2. So number 4, tank contains 500 gallons of a salt water solution containing 0.05 pounds of salt per gallon of water. We have pure water poured into the tank, and a drainage bottom tank is just so as to keep the volume of solution in tank constant. At what rate, gallon per minute, should the water be poured into the tank to lower the salt concentration to 0.01 pound per gallon of water in under 1 hour? So this one's a little bit more tricky. So c of t is x of t divided by v of t, which we've been using kind of implicitly, but not needing to worry about what c of t is. So that's concentration, salt, and mixture t minutes after the process begins. So again, no change in volume. So v of t equals v0, which is 500 gallons. We also know dv dt equals 0 means that that's also equal to rate mixture in minus rate mixture out. So we can say R1 minus R2 is equal to 0, or R2 equals R1 if you add R2 to both sides. So we can just say big R is equal to R1 equal to R2. We have to solve for R after all. That's the rate, gallon per minute. So dx dt is rate minus rate, so rate in, rate out, the salt. And it's going in at 0 because it's pure water being poured in. And that's basically concentration at time t times R2. It'll be 0 times R1, so that's 0. And we can substitute that in just for R as we showed earlier. So it's dx dt equals negative x divided by 500 times R. Or negative R divided by 500 times x is dx dt. You can rearrange it many ways. Now there's possibly a second way to do this, but let's do the first way, which seems like the more official way they want you to do it, to some extent. So we know c of t is equal to x of t divided by 500. As we discussed previously, it's xt over v of t, and v of t is always 500. So that means if we take the derivative, it's c prime of t equals 1/500 dx dt, implicit derivative. If you remember implicit differentiation, that's basically the same idea here. And that means that 500 times c prime of t equals dx dt. So dx dt is equal to 500 times c prime of t. We also have dx dt equals negative r times x of t divided by 500 from before. So we can substitute this in. Dx dt is equal to 500 times c prime of t, which is equal to negative r times x of t divided by 500. Now, but we can also substitute this in for just c of t. So everything's in terms of c, of the concentration at time t. So it's 500 times c prime of t equals negative r times c of t. And we can divide by 500 to just get it c prime of t on the left hand side. Then we can put this into dc dt equals negative r 500 times c. Then we can do separate the variables, and eventually we'll get everything in terms of concentration c. And I just used lowercase symbol like letters. So I have C3 for the constant here because you would put C1 and C2 for it, then you have C3. Separate it from just the actual C, which is concentration. You should probably use A or D or something for it. Like eventually I use A for a constant. But yeah, you solve this like normal, and eventually you get just, without the absolute values, C equals A times E to the negative R divided by 500 times C. And C of 0 is equal to 0.05, as it was given. 0.05 pounds of salt per gallon of water was the initial concentration. So A is equal to 0.05 when you solve for it. Okay. And now we know we need C of 60 less than or equal to 0.01 pound per gallon. So 0.01 is equal to, so it has to be less than or equal to, so we'll just say equal to, because that's the bare minimum and stuff. So this is the slowest the rate can be, basically, because we need it to be under 1 hour. So we'll just consider the equals, and this will be what we get. So 0.01 is plugged in for C of t. It's equal to 0.05 times E to the negative R divided by 500 times 60. So times 60 we have, because 60 minutes. Time D. So we divide and take the natural log. So we have negative R divided by 500 times 60 is equal to natural log of 0.01 divided by 0.05. Plug into a calculator. Eventually we solve for R and get 13.41 gallons per minute. And that's what the rate should be. 13.41 gallons per minute. Now here's another possible method which gives the same answer at the end. R equals 13.41 gallons per minute. Now, I kind of do some trickery and we just basically convert units a little bit. So we start with dx dt equals negative R 500 times x, and we solve for x. So we're going to have concentration, we're going to have pounds of salt. So eventually we get the same equation essentially, but in terms of x and t instead of c and t. We get a very similar equation. The difference is that our constant A is going to be different. So it's x of 0 equals 0.05 pounds per gallon times 500 gallons. The volume's constant, so we just multiply 500 gallons. And we get x of 0 equal to 25 pounds. So x of 0 equals 25 equals a times e to the negative r of 500 times 0 right here. That should be a 0. So it's basically a equals 25 from there because e to the 0 is just 1. So we have x of t equals 25 times e to the negative r divided by 500 times t. And x of 60 is less than or equal to 0.01 pounds per gallon, which times 500 gallons equals 5 pounds. So we need x of 60 less than or equal to 5 pounds, and we solve it the same way, eventually getting r equals 13.41 gallons. So it works. Not sure. I'd say stick with this method. But hey, this is an additional one if you really are stuck. Just convert, because you can technically do that, especially easily. You can do this with constant volume at the very least. It makes sense. Convert from concentration to just the pounds of salt. But that's how you do that problem. And the last one is a 50-gallon tank initially contains 20 gallons of pure water. Salt water solution containing 0.5 pounds of salt for each gallon of water begins entering the tank at a rate of 4 gallons per minute. Simultaneously, a drain is opened at the bottom of the tank, allowing the salt water solution to leave the tank at a rate of 2 gallons per minute. What is the salt content in the tank at the precise moment that the tank is full of salt water solution? So the VDT this time. So we want to find at the precise moment that the tank is full of saltwater solution. So the VDT is 4 gallons per minute minus 2 gallons per minute, so it's 2 gallons per minute. Now we can do a proper integration real quick about this. So it's dVdt equals 2. We do separation variables. It's integral dV equals 2 times integral dt. So V equals 2t plus c. So that means that, and we can also solve for V. So V of 0 is equal to 20. Which is equal to 2 times 0 plus c, so c equals 20. If it wasn't obvious, we're going to start off with 20 gallons. And that'll be c's constant in a simple linear equation like this. So v of t is equal to 2 times t plus 20. I mean, it makes a lot of sense. You start off with initial amount, you're just adding, it's basically changing by a rate of 2 gallons per minute. So it's a very simple equation. But it's more complicated than before where we just had a single constant. Now it's 2t plus 20. And the 50-gallon tank will come in play at the end. But for right now we want an equation for the salt content in pounds. Pounds related to time. So the xct is equal to 0.5 pounds per gallon as given, times 4 gallons per minute. So that's how it's entering, minus x of t divided by v of t times 2 gallons per minute. So 2 pounds per minute is what we get, minus x pounds divided by 2t plus 20, 2t plus 20 gallons times 2 gallons per minute. So what we ultimately have is 2 minus 2 divided by 2t plus 20 times x. So what are dxg? And we can simplify this further by dividing out 2 in the top, the numerator and denominator can divide out a 2 to cancel out. So it's 2, the xct equals 2 minus, in a term, 1 divided by t plus 10 times x. So that's what, and we can put this in terms of x prime and x, so it's a linear ODE. The a of t is equal to negative 1 divided by t plus 10, and f of t is equal to 2. The integrating factor will be, it's going to cut off a little bit mixed. So u of t, it's equal to e to the integral 1 divided by t plus 10 dt, and we're going to have to solve this. Cut off just slightly. So x prime equals, we rewrote it here, so it's u of t again. So integral 1 divided by t plus 10 dt. So w equals t plus 10, dw equals dt, so solve it. We have ln w, absolute value w, so it's absolute value t plus 10. And we can assume, since time is going to always be positive, that this will always be positive. So we drop the absolute value. I'll just have t plus 10 for this modeling exercise. Yeah, because you can't have negative time. So t plus 10 will always be positive, because the lowest it can be is 0, so it's going to be 10. So when we solve, we have 2t plus 20 dt. We have to integrate. All divided by t plus 10. This is easily solved, so because 2t is 2 times t squared divided by 2, so just t squared, plus 20, which is just 20 times t. When you integrate 20, it's just 20 times t. And plus e, I put e as a constant. It's all divided by t plus 10. So t squared plus 20t plus e divided by t plus 10 is what x of t is equal to. And we can solve for e pretty easily by putting x of 0, and it's equal to 0 because it's initially 20 gallons of pure water. And so 0 is equal to every t term being 0, so 0 equals to 0 plus e divided by 0 plus 10. 0 is equal to e divided by 10 basically, so multiply by 10, it's e equals 0. So x of t equals t squared plus 20t divided by t plus 10. So the tank V of t equals 50, so that's a full tank. So V of t equals 50 which is equal to 2t plus 20 if we want to solve for t here. How much time it takes to fill. And you get t equals 30 divided by 2, which is 15. So 15 minutes to fill tank. And that's what we want to know is, like, what is the salt content in the tank at the precise moment that the tank is full of saltwater solution? So x of 15 is equal to 15 squared plus 20 times 15 divided by 15 plus 10. You end up with 525 divided by 25, which is equal to 21 pounds. And that's the answer. 21 pounds of salt will be present when the tank is full. And that's it for those types of problems. Again, mixing problems are interesting in a lot of ways, but can be a little bit annoying sometimes if you have not practiced a little on them. The setup, they can be a little bit tricky sometimes to set up, as you've seen.